course, a lot of systems these days of all types are mechatronic systems. Almost every product, almost every system has a combination of mechanical parts to it, which you're learning about in mechanical engineering, but also it has electrical or electronic parts. It has control systems elements, or at least condition monitoring elements. The aim of this course is to provide students with the capability, or provide them with capability, that's you all, to provide you with capability in the fundamentals of classical control theory and also in the basic tools for control system design. So it is, I see this sort of as a design course actually, because the design of a control system for a product, or for any kind of system it's very much defines its characteristics and how it behaves, how it performs as a system. So the design of the control system is integral to the design of the overall any kind of mechatronic system. Right, so we're going to introduce you to this classical control theory. There are certain, and the way I describe it usually is this, like control systems is a bunch of tools in the toolbox that helps you to sort of work on your control design. So I'm going to introduce you to these different tools and let you practice using them, both using them by hand and also using them using computer tools, which is the MATLAB Simulink. In reality, if you were sort of in industry doing a control system, dealing with a control system problem, you wouldn't really use the hand methods, you'd use the computer applications. The reason we do the hand methods is just so you understand it and you're not just using the tools on MATLAB Simulink without knowledge and understanding. These are our objectives. So once you've completed this course, you should be able to ... demonstrate the correct use of standard control systems technology terminology, so get the lingo. This level 3 just corresponds to the what's called the Bloom's learning taxonomy. So I think learning level 3 is understanding, right? So the higher the level, the more critical the thought or the skill required to be demonstrated. So second objective for this course is that you would be able to determine and justify the most appropriate form of control system for different industrial manufacturing and product applications. So regardless of what system you're dealing with, what's the best type of system control approach to implement in each situation. Third learning outcome is that you should be able to create from first principles mathematical models. This one is a really good one and very important because we live in the age of digitalization, we live in the age of Industry 4.0, so one of the tools, as you would have learned in instrumentation, one of the core technologies that's associated with Industry 4.0 is the digital twin. And in control systems, we've been using digital twins for quite a while, so that you could design your control system and actually implement it even in hardware, while the hardware, which is your control system, that will be like your controller, which you program, you might connect that actually to a computer simulation of the plant or of the system that you're controlling. So the digital twin concept has been around in control systems for quite a long time, and is known, and it could either be that you have both the controller and the plant or the system modeled, and both there are models for both elements, or it could be that you have a model for the plant or the system and you have a hardware controller, so you can actually do a lot of controller programming and troubleshooting and debugging whilst using a computer model of your system. So this issue in number 3 here of being able to create those mathematical models is quite an important one. We'll do some basic models, nothing too complex, but really modeling is a matter of going to first principles and building up from there. So for that reason, we will be using in this course, it kind of synthesizes a lot of the things you've done so far, because the systems we model and we control might be mechanical, dynamic systems. They might involve the vibrations work you're doing at the same time as this will directly map into control systems. There'll be thermal systems which you have to control. There might be fluidic systems you have to control. Be motors. So a lot of the things you do in other courses, electrical technology and so on, all come in, and you'd be using all that information, even maths, because we have quite a bit of maths in this course as well, especially using Laplace transforms, which you may or may not have covered yet, but you should have covered, I think, already in your maths. I generally ask them to cover that in time for us to do this course. So all that being pulled together into this course, and modeling is a good challenge. It's a good challenge. In practice, again, if you're using control system design or doing control system design in industry, or even in postgraduate studies or something like that, you would probably, you might not build your model from scratch. You might use a library model that's available somewhere, MATLAB Simulink model, for instance, and just use that library model, adapt it and adjust it to your purposes. But you still need to be able to get the model, understand how it works, and make appropriate adaptations, and then basically validate it to make sure it's behaving as the physical system does. So all of that under modeling. And then fourth objective for this course is to be able to, by the time you finish, you should be able to calculate time domain behavior of basic control systems. So what we're talking about here is, how does the system respond in time? Does it, when you apply a certain input to the system, what's the output, or what's the reaction of the system to the input you've given? But also in a steady state where there's a fixed input, what's the fixed output of the system? Does the system match exactly the demanded input, or is there an offset? Is there a steady state error, as we call it, that's that manifests or happens through that particular control system? So we're looking at time domain response, and then we get into some more tools in our toolkit in number 5, which is looking at control system design and analysis tools. One of which is Evans root locus, and the other is called the Bode plot or Bode plot methods. So both of those methods you'll be looking at, you'll be using them, learning how to use them. They're available in the MATLAB control systems toolbox as well. So you can both do the hand calcs in these cases, and also use MATLAB Simulink to generate root locus, to generate Bode plots, and that allows you to in both cases, to interpret, to use those to understand how your system is behaving. All right, number 6. By the end of this course, you should be able to, this is like the pinnacle, design and implement a basic control system for a physical system using the MATLAB control system toolbox that meets defined performance measures. Now, those performance measures are things like, okay, if the input to a system goes from 0 to 1, we call that a step input, and in no time, just like bang, a demand, immediate demand on the system. How does the system respond? Okay, so it might, how long does it take to get to, say, within a few percentage of its final value? Does it have overshoot? Does it oscillate? And you can actually quantify those different responses, and based on those responses, that basically indicates how well your control system is performing and how well it does what it's intended to do. So you actually have to design a control system that meets defined performance measures, and you do that in the lab. That's tested in the lab, because you're actually asked to design a PID, or that's the type of control system that allows you to control a simple system to achieve certain performance criteria. All right, so this is how our course is structured. For the summer program, the schedule will be a bit different because the semester weeks don't apply. So the new schedule will look a bit like this. Since we already have our lectures recorded and available online, all our lecture sessions will be asynchronous. So basically what I want you to do is go back over the lectures during the period assigned for those particular lectures, So in week 1, you'll be dealing with the introduction of class transforms, block diagrams, and then each week, and the first 4 weeks, on Friday between 10 and 1, we're going to have our online Zoom-based tutorial. And basically for each lecture or each group of lectures, I'll be providing you with a tutorial sheet, and that tutorial sheet will have questions. I want you to go through those questions, try and answer them, and then in coming together on the Fridays, we're going to look at those together. Now the associate professionals in the department are going to assist with that as tutors, so they're going to be the ones really helping you in those tutorials on the Fridays. In the last week, we also have a revision tutorial, so that gives a chance to mop up any aspects you're not clear on. And then on the Wednesday of the last week, the 13th of July, you're going to have an in-course test. We're not sure yet whether that will be on My e-learning or face-to-face. It might be either, so be prepared for both options. That'll be from 10 till 12 on Wednesday the 13th. So that's the structure that we're looking at for this summer program, basically over 5 weeks starting from the 13th of June. And as I said, it's asynchronous, so you could just go through the lectures in your own time on the date specified, and then attempt those tutorial questions in time to come together on the Friday of each week to review them. This is a very quick reminder of the recipe for success for this and I think all your courses. I want you to make sure you attend all lectures. Well, in the case of the summer program, that means make sure you review all the lectures on the specified days. Do take your own notes, do ask questions. I am available. You could use both My e-learning and also the WhatsApp group to ask questions. Also use the textbooks. We'll talk about those in just a second. They can also be very useful to you to reinforce concepts or grasp things you don't understand. Complete all the tutorial questions in advance of the Friday tutorials, and make sure you allow adequate time for revision. So just a reminder of those things if you want to be successful in the course. All right, textbooks. These are the 3 textbooks for this course. Ogata is the first one, Modern Control Engineering. This is the main text, the 5th edition. I believe it's available around the place, so if you check out in cyberspace, you might find it somewhere. Right, so that one is quite good. It's quite wordy, I would say. You have to kind of wade through a lot of descriptive text to get to the core issues, but if you do it and you use that book well, it'll really give you a solid understanding. And these 2 on the right, these are sort of optional extras, and both of them are quite good in their own ways. So I could recommend both of these as well. And I think if you look online on the course outline, I've actually identified which chapters in each of these books correspond to each section that we do in the course. So you can basically go and read through the chapter, try some of the problems, look at the worked examples in the book. Some of the worked examples in the book you'll probably find turning up in my classes as well. All right, so these are the 3 books that we use for this. All right, let me stop there and see if we have any questions at that point. Anyone got any comments, questions, or anything like that? No? You all good so far? All right. Okay, well, let's press on then. In fact, one more admin thing. I'm just going to give me 1 second here. I'm going to set up a WhatsApp group. Just give you a little moment here, just talk amongst yourselves. All right, here we go. Right, WhatsApp group there. You can just click on that link and join the WhatsApp group that I just created. You could also copy it and paste it and distribute it. So this is specifically to allow quick and easy communication through the semester. All right, so let's press on. Got a couple of videos here to show you. So by way of introduction to control engineering, I'm going to look at some examples of interesting controlled systems. The first one is particularly close to my heart. I have one of these and I find this really cool. So I thought I'd share it with you. It's basically an advert for a robot vac. So here we go. And I like this one because it has a lot of fairly detailed controls in it. So this is actually an autonomous system, effectively. And it's a little kind of just fanciness, right? So just a little marketing thing.
D-bot, start cleaning.
So this thing maps its environment and it navigates its way. Navigates its way around. It can see, uses a laser, a LiDAR system to be able to map its system and then navigate its way through. So it has sensors like on the front and underneath the device, which, like as soon as, for instance, if it goes over to the edge of a step, that it's going to fall down, it'll sense that and pull away. It also has to design or determine, you see this map here, so based on that, the way it's mapped out the environment using the LiDAR, it now has to decide how to optimize its movements, optimize its cleaning within that environment to get complete cleaning in the fastest time possible. So all of that's kind of what the D-bot does. There are a lot of these different types of robot vacs now, and that's just one of them. So I find that's pretty cool. It's a very nice example of a control system. Of course, the speed of movement and all that sort of thing has to be controlled. How do you control the trajectory or the direction of movement of that device? It has to control its speed, has to control its direction. So you've got two wheels, one on either side that can counter-rotate to give like a full 360 rotation. All of that, of course, is being controlled as well. Right, so that's a good example of control system. Of course, inside the circuit board, there's a bunch of programming that's gone into making all that control activity happen. So, for instance, what happens when it detects, when one of its bumpers is activated, it detects an object, and it can't follow the trajectory it expects to follow. How then does the device navigate its way around that? That's all a bunch of control algorithms and things that have to be written into code to allow it to manage its movement. Here's another one.
Adaptive cruise control helps maintain an individually stored.
Sorry, are you hearing okay, by the way? This one has a bit of a commentary, so. You hearing the commentary? Yeah, okay. I think it might, I don't think I'm sharing my sound, but I think you might be able to pick it up from my speakers.
Constant speed between about 20 miles per hour and 95 miles per hour. at a previously set distance in time intervals between your vehicle and those in front of you. To switch on adaptive cruise control, press the on-off button on your steering wheel. The system is now active, but no speed is set. To save the current speed when the vehicle is moving, press the Set button. The set speed appears in the instrument cluster, and the adaptive cruise control system begins regulating the speed to help automatically maintain a comfortable following distance to a vehicle in front. The adaptive cruise control system helps maintain the following distance by determining a time interval, resulting in a speed-dependent distance. When adaptive cruise control is active, the following distance to the vehicle in front can be adjusted to one of 5 positions by pressing the adaptive distance button. The distance intervals can also be set using the plus or minus buttons immediately after pressing the adaptive distance button. When a slower moving vehicle directly ahead is detected, adaptive cruise control automatically slows down and helps maintain the distance that has been set. Once the slower vehicle moves out of the way, the system adjusts back to the set speed. If the vehicle traveling ahead brakes to a standstill, adaptive cruise control will also brake your vehicle to a standstill. The driver assist system holds your vehicle stationary, with the brakes and adaptive cruise control staying active. To drive off after being stationary, briefly press the accelerator. Adaptive cruise control will resume speed regulation as long as the vehicle in front is moving again. To deactivate cruise, briefly press the cruise on-off button on the steering wheel, or press the brake pedal. To resume the stored speed, press the resume button. To increase the speed by 1 mile per hour, briefly press the plus button, or press and hold to increase the set speed in increments of 5 miles per hour. Press the minus button briefly to reduce speed by 1 mile per hour, or press and hold to reduce the set speed in increments of 5 miles per hour. In addition to the functions of a traditional cruise control system, adaptive cruise control can help speed up or slow down your car to keep a comfortable following distance to the car ahead.
All right, so I shared that one with you because that's cruise control is a classic and almost like a good model of a control system. So the one here is a slightly enhanced version because it allows you to keep a certain distance from the car in front and to slow down and speed up, or to basically modulate the set point speed according to the distance behind the car in front. But a classical, basic control system allows you to set a cruise speed, and then it will hold that speed. So, for instance, if a vehicle starts going up a hill, it would automatically slow down. So the cruise control system then would accelerate the vehicle, or would give more torque to the engine or to the motor to keep the set speed. If the vehicle is going downhill and starts to accelerate, it would ease back on the the torque from the engine or from the motor to slow the vehicle down and try to bring it back to its set speed. So it has some good control system elements to it, like set point, which is the desired condition you're trying to aim for. Response, because some cruise controls would respond more aggressively than others and accelerate the car harder than others. And then with this one, you see it has that additional element of keeping the car a certain speed, a certain distance from the car in front, slowing your car down when it does. Of course, this is like the stepping stone towards more autonomous driving. And that's really, if you're tracking Tesla at all, that's where Tesla's going now. Last year, they've had this autopilot system for a few years, which isn't really all it's, it doesn't really live up to its name, because all that was kind of an enhanced version of the adaptive cruise control. It had lane keeping, and it had the adaptive cruise speed thing to it. But now they're moving into sort of full self-driving mode, and they're currently rolling out the beta version of that to selected customers, and that allows full autonomous driving. So that means you could basically have hands off the wheel driving. Still requires a driver in the driver's seat, but of course the amount of control system stuff that goes into something like autonomous driving is just phenomenal, because the vehicle has to be able to sense and interpret a very dynamic and unpredictable landscape. And just as we, you know, the very highly developed human brain, which has the capacity to interpret and process information and respond to the environment it's seeing and interpreting very dynamically, you know, for a machine to do that is a different level of requirement. And only now really are we getting to the point where you can kind of move into that autonomous driving domain. And it can only be done because of things like artificial intelligence, machine learning, and these kind of things, which say the Tesla system and other systems like the Waymo, they're building upon that. So all of that is very advanced, and I'm kind of giving again away for a question I'm going to ask just now, but those are sort of very advanced systems. So let's look at one more example. Like this one. Right, this one. So this is a student project. This is a totally different end of the spectrum. Let's have a look at this one.
Hey guys, this is our autonomous Follow Me cooler. It's basically an Arduino-powered robot, which follows you by connecting to your smartphone via Bluetooth.
It navigates by comparing its own location to your phone's location by streaming GPS coordinates. Here you can see the cooler following me around the park.
We built this using an Arduino Uno and some off-the-shelf hardware. It uses a customizable IoT app to interface with the cooler.
Let's say your friend is on the other side of the park, but you don't want to walk all the way over there. You can give the cooler a set of GPS waypoints so that it can make its way over there without following you.
That's not all. It also has a motorized lid. Cheers.
The cooler is removable, so you can also use the base to carry other things.
Hope you enjoyed this video. If you want to see how we made it, you can check out our 2 build videos.
We also posted a detailed set of instructions on hackster.io. It's a really cool website where you can view our 3D models, our code, and our schematics. We highly recommend that you check it out if you want to find out more about how to build this thing yourself. The links will be posted in the description if you're interested.
As always, if you want to stay up to date with all of our videos, make sure to subscribe. But until then, see you next time.
Let's look at some of the common elements in all those systems. So in every system, every control system, you always have an input or a target, what we also call a set point for the system. So that's where do we want the system to go? What's the reference point that we want to achieve from the system? It could be a system that's trying to reject instability or disturbances, and it's supposed to hold a certain point, like a cruise control system that's trying to hold a certain speed, regardless of the wind resistance varying, regardless of the gradient varying. It's trying to hold that same fixed point speed. So that would be a set point. Or it could be a system where that target is changing and you have to decide how the system is going to respond to a changing target, like with the follower cooler, where the person was walking and the cooler had to decide how to respond to the change in target location or target position it's trying to get to. What other elements are there? There's always a system that you are controlling, or we also call that a plant. That's called a plant because of industry plant, not an organic plant, right? So it comes from, you know, a kind of plant and machinery type plant, and there's always some system. So if it's a self-driving car, the car itself is the system. Right, so then there's also the output or performance. So if you've got a cruise control system in a car, the output is the speed of the current speed, the actual speed of the vehicle, and you're comparing that with the set point, which is the cruise control, the input, which is the cruise control target speed. The system is the car. And then you've got sensors which measure the performance. So a cruise control system, it would have speed sensors on the wheels. That would be what is used as the sensors to determine what is the current output or the current performance of the vehicle or of the system. I'll come back to that question, Ty. And then you're also always going to have a comparison between the current state and the desired state. So you've got your set point, your input is the desired, the feedback from the sensors is the, or the sensors give you the measured performance, and the feedback is the difference between the two. And then the control intelligence always works off the feedback. So the control intelligence will respond to the difference between the desired position or speed and the actual. And it will determine, based on the difference, how it's going to respond to that and what changes it's going to make to the plant, which is the system, to correct that difference between what you want and what you've got. Ty, you're asking about active aero. That's also, a good example of advanced system, but the thing with active aero is it's probably open loop, not closed loop. So when I say that, I mean it would be triggered by the vehicle reaching certain speeds, right? And because the aerodynamics is fairly speed dependent, so when a vehicle reaches, say, 50 miles per hour, a spoiler might rise, or a kind of a diffuser might close up or might change shape or something, but that would not really be a dynamic response to some feedback. It would just it would be triggered by a certain speed being achieved. So that would be described as an open loop system. And some of the systems we gave as examples from our household systems are actually also open loop. Like, say, a basic washing machine would have a cycle which is programmed. So the cycle would remain constant regardless of how many clothes are in the washing machine or whether water goes in or if there's no water. It doesn't, it would just proceed through its cycle because it's designed to just be triggered by time. So that would be an open loop type system, but and I think active aero would probably be open loop as well. Now let's look at some closed loop systems. And this is a control engineering definition here is the application of feedback to give improved dynamic behavior. So compared to an open loop system like what I just described, a feedback control or closed loop feedback system takes the senses the current state, compares it with the desired state or the set point, which provides the feedback, which is the difference, and then based on that feedback it applies a correction or tells the system how to adjust. So here's an example: a fighter jet, a statically unstable aircraft. So why would a fighter jet be unstable? Well, the reason for that is because of maneuverability and so on. So it being unstable means it's much more agile compared to, say, a commercial airline or commercial airplane, which is focused on comfort for the passengers, has slow response, very stable. If it gets disrupted by turbulence, it would tend to settle back to its, a stable condition. If the power goes from the engines, it would tend to cruise or to be able to glide fairly easily. But a fighter jet isn't like that. If something happens to a fighter jet, if the control system is not actively controlling it, it's going to go out of control basically, because it's statically unstable. It means it's really hard to control by hand if it was just the pilot trying to do it. Now, what makes it statically unstable is this diagram here showing that the center of gravity, which is marked here, is different from the center of lift on the wings, which means that the system, the aircraft will always want to rotate. Right, so that makes it unstable. So it can only be managed by the application of flap. or the tail fin, which creates a counter rotation through a negative lift and stops that rotation here happening. So the management of the flaps, the management of the ailerons on the tail fin and on the wing will correct that rotational instability, and that's being actively managed by a control system. All right, so if we have that statically unstable aircraft and it's disturbed by a gust or turbulence, even whilst the control column is held fixed, it's going to be very, this is the angle of the aircraft. It's going to rotate. It's going to have an oscillation before it settles back down. It's poor stability. This is convergent because it does eventually become stable. You can see the amplitude of the oscillations is declining over time, but it is oscillatory. It's what would be called lightly damped. If it was fully unstable, that means that when a disturbance acts on this system, it would actually cause it to have an increasing pitch angle as time goes on. This is kind of going out of control here, just flying out of control. So the pitch angle diverges and the aircraft goes out of control. So in both cases, we need to improve the stability and reduce the pilot workload to make the aircraft safe. So what we do here is we measure some key parameters and adjust the system behavior to modify the response of the system. And the key parameter in this case, pitch, that's the angle alpha here, is the pitch, the angle of the nose of the aircraft versus horizontal. And pitch rate is what's the rate of change of that angle. So we're looking at pitch rate and we're measuring pitch rate. How would you measure pitch rate? Any ideas? What kind of sensor would you use to measure pitch rate? Anyone think they know? Hey, correct, Mikhail. It's a gyroscope. That's right. So you'd use a gyroscope, and you would measure it using that. So if we don't have the feedback, and we have just an open loop system, then all that happens, the system is very straightforward. You have pilot demand, which is the yoke, which is the control system for the aircraft, and the pilot is demanding a pitch, certain angle of attack of the aircraft. That pilot demand, it might be an electronic yoke or electric yoke, but it activates a hydraulic actuator because aircraft, ailerons and so on are hydraulically actuated. So the electrical signal would be converted to a hydraulic actuation, and then the ailerons would change angle, and that of course affects the aircraft dynamics. So it's going to create a rate of change in the angle of attack or the pitch of the aircraft, and that's going to be a pitch rate. This is the open loop system. This depends entirely on the pilot and his instruments as he manages this system manually. This is called open loop, and this we've introduced here something called a block diagram. We're going to be using block diagrams extensively in our modeling aspect of the course. So a block diagram allows us, inside each of these blocks is basically a set of equations, right, that tell us how the output is related to the input. But we're able to just put a block and hide a bunch of equations inside each block and simplify the way we are presenting, the dynamics of a system. So here's a slightly more complex diagram. This one is a very fundamental diagram, block diagram that we're going to be using all the time as we go through the course. And this is adapting, going a step beyond our open loop system, and now we've got a closed loop system, because this is our system here, or our plant, and we're measuring the key parameter that we're trying to control, and we're feeding that measurement, we're measuring it using a sensor, and the sensor output is being compared using a comparator with the input or the set point, the target, to create an error, which is our feedback error. That then goes into our control intelligence, which might be a compensator. That's a type of controller. And the compensator is saying, okay, system, you need to adjust in this way or that way. So that becomes the input into the system. So in this case, for the aircraft we just looked at, the input, which is the set point, would be the pilot demand. That's compared with the current pitch rate, right? Using a rate gyro, as you correctly said, Mikhail. So that provides its current angle or current rate of change of pitch compared with the current demand, and that gives us an error signal. You see there's a negative sign here, so the value on this line is positive. It says negative feedback because it's going to be subtracted from the pilot demand. So if the pilot demand is, say, 10, your feedback is 5, the error will be 5, the controller gets an input of 5, and it decides, what am I going to do with this 5? It gives an output to the servo hydraulic actuator. This is called this is your actuator in the system that changes the angle of the ailerons, and then of course that's going to affect how the aircraft flies in the air and the rate of the pitch rate that's generated as a result. Right, so that's how a closed loop system would be working. So now when the pilot applies his demand, the difference between the current pitch measured from the pitch rate and the demanded pitch is going to be create this error signal, and the controller will start to automatically adjust the aircraft dynamics to match the pilot demand. The controller is set up so that it tries to minimize the error. So, yep, that's correct, Adidova. The feedback fixes the problem that the system experiences. That's the point of the feedback. It's able to kind of look at this difference, and the controller is designed, or the algorithm in the controller is supposed to close the gap between the current demand or the set point and the feedback as fast as it can, safely. Right, so it has to kind of fix this feedback part here towards 0 to make it error 0. So this shows what the potential response would be of a nicely designed control system. So this is the pilot's input, this solid black line. He gives a step input, kind of a bit aggressive. This pilot just moves instantaneously from position, let's say, position 0 to position 1. And the aircraft, now with this closed loop system, kind of manages its response. Now, if it was an open loop system, it might have overshot or even gone unstable. But now the closed loop system is trying to minimize this error, and it can't quite do it immediately, but it overshoots a bit, but then it's kind of quickly converges in a fairly safe and convenient way. So, good question. What will be the purpose of an open loop system? Well, to implement a closed loop system, it means you have to have the sensors, it means you have to have the controller, you have to design that controller, and so on. So it adds a lot of cost and complexity to any mechatronic system. So if you don't need it, you shouldn't put it, right? So the issue really is that it comes down to the fact that it should be something you only do if you really need to do it. But in most cases, a lot of cases, you would. So an example of not needing it, so if we take, for instance, let me think of a good example. Well, I would probably go again with the washing machine. The washing machine, in most cases, it's safe to cycle through this, go through the cycle without the feedback to the machine saying, okay, I've got 10 pounds of laundry in the machine, without saying, okay, it's sufficiently rinsed yet. I'm not detecting any more soap in the system. So once so a lot of systems or a number of systems can be designed in an open loop configuration for cost and complexity reasons. So from this first control example, what have we learnt? Firstly, that to design a control system, we need to do certain things. We have to, we're talking here about a closed loop feedback system as opposed to the open loop feedback system. First of all, we need to be able to measure a system response. You need some sensor, and you need to be able to get the output from that sensor, compare it to the set point. Right, so you have to be able to measure or quantify your system response, which is time-based. And then you have to be able to develop or have a way of doing your design your controller. So you have to be able to set up an algorithm in that controller block, this controller block here. What goes in here? How do you respond to a particular error? What exactly are you going to do in this controller? That's the big question for this course, really. How do we design a controller that gives a nice reaction of our system to a specific input? And this is where some of our tools come in, like, for instance, our root locus, frequency response, bode plots, these things that we're going to do with as we go through the course, right? We've got a tool set for actually designing what goes into that controller block. To design it, you have to know what the objective is. Are you trying to improve the stability of the system? Are you trying to improve the accuracy of the system? The accuracy is the difference between the set point and the steady state value. Are you trying to reject disturbances to make it respond faster? So there are a number of different potential objectives, and you have to know what you're trying to achieve, right? All right, so here's another example of an open loop system. We were asking about these earlier. This one's to control engine speed in a car, idle speed. And typically, in older systems, especially mechanical control, way back in the 1980s, we had something called carburetors in car engines, which is a way of mixing your engine, your fuel and your air. And you'd have to adjust your idle speed by tuning a tiny little screw on your carburetor that allowed more or less fuel through, and that would change the idle speed of the engine. And that was basically an open loop engine idle speed system on vehicles, right? And you demanded then idle speed would be basically what you want to achieve, so that would be the set point. You'd adjust that with a little screw on the carburetor itself. The actuator would be the carburetor, which allows a certain air to fuel ratio, or let's say charged air with fuel in it into the engine itself. And that would cause the engine to either accelerate or decelerate or whatever as it idles. Now, the problem with an open loop system generally, especially on something that has, potentially got sort of is a variable system and a dynamic system, is that if you have a disturbance, like say your AC turns on, right? So the air conditioning on a car puts quite a big load on the engine. It's actuated by a clutch, so when the compressor needs to turn on and the clutch engages and it starts to spin up that compressor, it puts a big load on the engine, especially when it's at idle. So that would pull torque out of the engine, and it would want to slow down. In a sense, it kind of increases the effective inertia of the engine, and therefore will try to slow it down. So you end up with an idle speed after the AC turns on, which is lower than the demanded or set point engine speed, and there's nothing much you can do about that. All right, so what does that mean? If you assume that you're wanting to idle at, say, 700 RPM, revs per minute, and then the AC compressor cuts in, how is this open loop system going to respond? Well, the open loop system might be a bit oscillatory. this sort of hunting around a bit, speeding up, slowing down. But when this load comes on, it'll pull the speed down. If it pulls it below a critical point, then the engine will actually stall, right? Which is obviously a kind of what you might describe as a catastrophic error. So this is a weakness of an open loop system. It doesn't have the capacity to recognize that the current performance of the system is deviating significantly from the set point and adapt and apply a correction to prevent that error from happening. So that's under an open loop, which is kind of how it always used to be back in the day. Now you could overcome that by increasing the idle speed. So if you increase the idle speed to 1000 RPM, when that load torque came in, it might drop down sort of like this. So you might be up here instead. And when the load torque comes in, instead of going down below stall, it just kind of drops down here somewhere. Right? So it doesn't stall, but it's still way below your set point. The problem with that is what? If you set your idle speed higher, what's going to happen? What are you going to be using more of? More emissions, more fuel, exactly. Right, so you're going to actually, especially at idle, say you're in traffic and idling in traffic, you're putting out a lot more toxic emissions from your exhaust tailpipe and so on, right? So what can we do? I'll wrap this up, I'll finish this example and then we'll stop for the day. Well, this is where you can implement a closed loop negative feedback system. So that will allow the demanded idle speed to reject disturbances. So now instead of the open loop, we'll just skip back. This is what we had with an open loop system. Nothing could, the disturbance would happen and the system wouldn't know what happened, wouldn't be able to respond. But now we're going to have the same disturbance, same engine dynamics, same actuator, but now we have a sensor. The sensor in this case would be a tachometer, speed sensor. And that creates a negative feedback compared with the demanded idle speed. So now you have an error going into your controller, and the controller now manages the actuator. So effectively, this can be implemented instead of using a carburetor, you're now using, say, a throttle. And you can open the throttle if you find that the engine speed starts to go down and you have a kind of negative error here, or a positive error, then you could open up the throttle a bit, which is the actuator, and then the engine will accelerate and catch itself before it stalls. So now, if you have your 700 RPM idle speed, now the load comes on at this point, the negative feedback recognizes a kind of a negative or an error is created here. So that applies an action to the actuator, and the actuator might in this case be the throttle. It opens up, allows more air and more fuel into the system, and then it is able to catch itself and stabilize itself. Right, so a control law has been selected that gives zero steady state error. It tries to manage any disturbances to minimize steady state error coming in. This example is actually a simple example, very simple. So in this case, you have a disk, a load inertia, and you have to control the angular velocity of this load inertia, right? So an example of how this might be used is, for instance, if this was the base of a satellite receiver, receiver dish, and it rotated. So you want to rotate to a given fixed position, a very precise position. Or you want to be rotating. You remember how those satellite dishes, sometimes you see them spinning, like the rate, well, that would be more like a radar receiver. So in that case, you want to control the angular velocity. So just a couple of examples of how this might tie to real life. But in our case, we just have the disk alone. There's nothing on it, but we still want to be able to control the angular velocity of that disk. And we want it to be able to resist disturbances and give a good response to changing inputs. So if we want an acceleration to a higher velocity, angular velocity, or if we want it to decelerate to a lower angular velocity, then we want that target or that new set point to be met. And we also want it to have, in steady state, we want the speed to equal precisely without an error the set point. That's number 2 there. And the third one is if something happens, if the wind blows or if someone puts their finger on the disk to add friction, then we want it the system to reject that disturbance and maintain the speed, just like the engine speed example we looked at on Tuesday. Right? So this is an open loop block diagram showing this system. Remember, blocks, basically behind a block is just a set of equations that describes the behavior of a particular part of the system. So we can break the system down into parts, and each part could be represented as a block. So any block has an input on the left usually, and then an output on the other side of the block, and the input is manipulated by whatever the transfer function is within the block, whatever the equation is within the block to create the output. So in this case, our demand, that's what speed we want this disk to rotate at, is fed into an actuator, and the actuator in this case is a DC motor, and the voltage is related to the rotational angular velocity. So if we increase the voltage, we expect that the rotational velocity will be increased. We don't know whether it's linear or non-linear, but we do know there's a relationship between increasing velocity corresponds to increasing voltage. Then in our block diagram, we have the representation of a disturbance acting on our system. And this disturbance could be a load torque. So as the DC motor applies a given torque to the load inertia, torque is like rotational force, and so as you apply torque, you're going to create rotational acceleration. But then there's also a disturbance that's acting on this. It could be positive or negative, so it's represented as a positive here. If it's a disturbance which increases the load or reduces the torque, then the disturbance itself will be a negative. So the sum torque is what actually accelerates the load inertia. So behind this block, the equations behind here would be the equations of motion, Newton's second law, expressed in a rotational form, in other words. So that's and then out of that we get the angular velocity as the output. So that's the open loop system. Now, of course, what happens here is if the disturbance is applied to this system, the system doesn't know that a disturbance is being applied, and so the inertia will respond to the net torque, and the output velocity will reduce. So there's no ability within this system to resist or to compensate for a disturbance that's being applied. So we can say at this point, certainly number 3 is not going to be fulfilled as a design requirement or a measure of the goodness or the performance of this control system. So we want to do something about that. If we apply a step input, then this is the diagram representing, or the graph representing that step input. This is input, this is time. That's the initial input is V1, a lower voltage. At time T1, that voltage gets instantaneously increased to a new level, V2. So this is what's called a step input. Now, we use step inputs a lot in controls because it allows for for us to test the system effectively. It's a fairly extreme input, but by applying a step input, we could look at the response of the system and learn certain things about its characteristics, right? So this is a typical input, step input that's being applied, an instantaneous change in the input voltage on this motor, which then is connected rigidly to the disk, the solid disk. So what's the response? Well, the black lines are input, now the dotted line is our output. And we can see that with this open loop system, when you make a step input, you kind of get a gradual acceleration of the output speed of the disk. So this is what would be described as a sluggish response. And what's more, we can see that when time goes to a higher value, let's say towards infinity, then the output never actually reaches the input. There's a gap here, which is called a steady state error. And so the open loop system doesn't do very well for number 1, which is the speed of the response. And it also doesn't do very well for number 2, which is steady state accuracy, because in the steady state condition, there is in fact an error. And we already said it doesn't do very well for disturbance rejection either. This is a disturbance example. Oh, too many. There. All right, this is a disturbance example. So now our input, our disturbance is sort of being switched on and off. So you could basically assume for our disk, it's just a little disk about this big that we use in the lab. We'll use that as an example. I should have put a picture of it in here, but it's mounted on top of a motor in a box, and so this disk is spinning. The disturbance in this case could be you putting your finger on the disk to slow it down, taking it off, and letting it accelerate again. So basically, every time you apply a disturbance, you see that there's a change in the speed of the disk, and you're getting a kind of an input square wave pattern, creating an output sawtooth pattern. And that sawtooth pattern is basically because every time you apply the disturbance, it's like changing the input, and you're getting a sort of what would be described as a single order response here, which is quite sluggish. So you just get a series of single order responses which accelerate the disk when you take the load off, or the disturbance is removed when it's applied. Oops, it starts to decelerate the disk again till it's removed, and so you get this sawtooth pattern, right? So that's what we're looking at here with the disturbance. Let's now apply our control engineering, and by that we mean applying a feedback loop. So we've now made this a closed loop feedback system. And how did we do that? Well, we attached a sensor to our output, which is to measure angular velocity. So we've now found a way to measure angular velocity. We're doing that using a sensor, which is a tachometer. And so our loop speed, or our inertia speed, or a little disk, we can measure it. That feeds back and is compared with the demand in what's called a comparator. So we're now comparing the measured speed with the input speed, and it's negative feedback. So you always subtract the feedback from the set point, from the demand. All right, so so now we'll have an error, which is the difference between what we're asking for and what we're getting. So if what we're getting is less than what we're asking for, then there will be a positive error because it's negative feedback. So it means that we'll get a positive error. If our feedback is of a higher value than what we're asking for, then there will be a smaller plus minus a larger value. So you get a negative error. So if we have a positive error, in other words, it's going slower than we want it to, then the controller will multiply that positive number by its algorithm. So you get an increase in your control action. If it's a negative feedback, then when you multiply it by the controller action, you're going to get a negative control action. And in that case, the actuator voltage will be instructed to reduce, right? Or a reduced voltage will come from the controller to the actuator to slow down, or to cause a reduction in the torque being generated by the DC motor, which is applied to the load inertia. So you're slowing down the whole system. If it's a positive error, which means that it's going more slowly than you want it to, then you get a positive control action, which means you're adding voltage to the DC motor. You're adding voltage, you're adding torque output. If you're adding torque output, you're going to accelerate the inertia. Okay, so now our response of our system is going to be quite different because it's constantly monitoring itself and trying to adjust and adapt to the changing output conditions. So let's look first of all at what we call the transient response. So this is how quickly the system responds to and how stably the system responds to changing inputs or changing disturbances. So the transient response, and we looked at this with the aircraft example as well. If you have an unstable response, then you have an output something like this, not a very well drawn graph, but basically as time goes on, your output is increasing in magnitude. You know, ideally what you want is when you have a step demand like this, over time your output will converge towards that step demand. But what's happening here is when you apply the step on this system, the output's actually oscillating, but the oscillations are getting bigger and bigger until it goes totally out of control. This is an unstable example of a transient response. We don't want that. That will only happen if you have maybe a particular type of system with a very aggressive controller. Another type of output that you might have for your transient response is going to be a very stable response, which is a bit sluggish. That's something like what we saw with the open loop system, right? A sluggish response. So that's not a very good transient response either, right? It's a bit too slow. Or we could have what's called a fast stable response, which means that you get a pretty quick response to your step command, your step input, and plus the system settles down to match the demanded input in a fairly reasonable time frame. Right? And so this fast stable response, this is the kind of ideal that we're looking for. We're looking for something like this. You want to sort of minimize your overshoot most of the time, and you want it to converge as accurately as possible and as quickly as possible to the set point. So this is what we're looking for. Now, can we then tune our feedback controller, our closed loop feedback controlled system, to give us this, a fast stable response? And the course really, this whole course is sort of looking at how we go about tweaking our control systems to give us a desirable output from the system, transient output, and what we'll look at in just a second is our steady state output as well. This is what the system is like in the open loop condition, or something like this, sluggish, but we want to adjust it now using the closed loop feedback to make it a bit more like this. Then the other aspect of specifying our control systems, look, first of all, we want to use our controller, our feedback controller, to get a good transient response, but we also want to use it to give us a good steady state error response, or a good accuracy and good disturbance rejection. High gain controllers reduce steady state errors. So the bigger, if I just skip back here, the larger the gain or the multiplying effect of the controller on the error, then the less error you're going to get at your output. But there's a trade-off, because the bigger your gain of your controller or your multiplying effect, then is also going to make the system less stable. So there's a trade-off between reducing your steady state error, because you want a high gain system to do that, but then that could also create a less stable system. So you have to decide, and this is part of your trade-off decision making and design process, and as you're doing your control engineering, is how do you get that right balance point. So high gain controllers reduce steady state errors, and they're better able to also reject disturbances, unknown disturbances. But as I said, this is at the cost of reducing stability. So this is a large error and a sluggish response system. This would probably be let's say typically a low gain system. If we increase the gain of that controller, which is the multiplying effect now, what do we get? We get a smaller steady state error, but at the price of stability. We also get a faster response, but you can see it's a lot more oscillatory. That's not necessarily a good thing. So from this first lecture, we've gone through the basics, apart from introducing the course, which I spent some time doing. On Tuesday, we've gone through some of the basics of control systems. We learned about open loop and closed loop feedback systems, and we've learned a little bit about the kind of things we're trying to achieve with our system as well, in terms of its transient response, but also its steady state response and its ability to reject disturbances. So what we've learned is that we need some form of representing the system. We need something, some way of drawing it. And the way we do that in control system engineering is that we use a block diagram, usually. There's another way that we sometimes can also represent our system called, but we're not going to look at that one. That's, I was thinking state flow. It's not state flow. It's the signal flow graphs. But we're not looking at signal flow graphs. I used to teach that, but I took it out because I was trying to reduce a little bit the content in the course. So we're only looking at block diagrams. That's the main way that you represent control systems, to be honest. So that's what we do. Right, so we're using block diagrams, and that's better than using engineering drawings or other representations for control systems. What else do we need apart from being able to represent the system or draw it somehow? We also need test signals. So these are standardized inputs that effectively energize our system and allow us to see how it responds to these different types of inputs. And our test signals can be impulse, which is just an instantaneous pulse of energy being input to the system. It could be a step input, which is an instantaneous change from one input, could be 0, to a known other input, could be 1, or it could be a lower value to a higher value, or a higher value to a lower value. That the importance here is that with the step input, you have a fixed input, value 1, instantaneously changing at some known time to a fixed input 2. You could also test a system with a ramp input. A ramp input is increasing an input which increases linearly over time. So it might start out at 0 and then be growing, basically into infinity in a straight line manner. So your input is ramping up. Then you could also have sinusoidal inputs. So there's a kind of 4 standard test signals that could be applied. Sinusoidal inputs, we use that a lot when we're doing frequency analysis, because when you're applying a sinusoidal input, you can see what the frequency response of a system, including its control system, is, and we could learn a lot about how a system behaves by looking at its frequency response. So we can apply a known frequency of known magnitude at the input. If we measure the output frequency and magnitude as the system is oscillating, then we can actually learn about the dynamics of the system by comparing that input and output. And we also need, what else do we need? We need ways, like I said, of analyzing the system's dynamic performance and how good or bad our controller design is. You know, is the controller allowing us to get the system to behave how we want it to behave? We also need a mathematical model of the system's dynamic behavior. And that mathematical model, there are 2 fundamental ways you can derive a mathematical model. You could either go from first principles and build it up with its differential equations, or another way to get a mathematical model is called empirically. And to get a model empirically, you measure behavior of the system by giving it known inputs, measuring its outputs, and then by comparing those, you could derive the transfer function or the relationship of behavior, the kind of controlling, governing equations of that system by using your experimental data. Right? So there are 2 ways, either experimentally derived or empirically derived models, or analytical, which is basing your modeling effort on first principles. When we're specifying our control systems, this is like the flow, if you like, the process flow. First of all, we have to get our system dynamic behavior. We have to understand what it is, either by measurement or by deriving from first principles. Then we can create a mathematical model. Once we have our mathematical model, then we can do our analysis and design. And as I was saying on Tuesday, what we're doing in this course is kind of creating a toolbox full of tools that we can use to do these different parts of the process of actually being able to specify or design a control system for a particular system. So here are some of the tools in the toolbox to mathematically model the system's dynamic behavior. We can use differential equations, which we then transform using Laplace transforms. And once we've got our Laplace transforms, we can create our block diagrams. So our block diagrams basically represent our system in the Laplace form. Then for the analysis and design, and there'll be a lot of work that we do on our analysis and design tools to understand how these tools work and how we can use them. One is Routh-Howitz. That's basically a way of determining stability of a system. Root locus, Bode diagrams, Nyquist, and Nichols. These last two, Nyquist and Nichols, we don't deal with those, but these three, Routh-Howitz, root locus, Bode, we use all of those, right, to analyze our system. And of course, there are other tools which we'll come to a bit later, like different ways we can create a controller or implement a controller, and we'll learn about those as well. Then we'll analyze it using these same tools and see how our controller design affects the overall dynamic system behavior. So that's just a kind of overview to wrap up the introduction.